Section 1-7 is proofs about integers. This is a very light introduction to a field of mathematics called number theory. And let's just sort of dive in here and say a conjecture is a statement that we believe may be true but have not proved. So a conjecture is basically an educated guess that something is true, but we haven't proved it yet. So that's our starting point, really. We're going to define a couple of things that you already know the definitions of, or at least I think you do. An integer is even if and only if. When you see that, you know you're talking about a definition. An integer is even if and only if it's equal to 2 times something for some integer k. And that's exactly what you already know. The other way to think about this is if you divide both sides by 2, you get n over 2 is equal to k, and k is an integer. Essentially, you're saying n is divisible by 2, but then we'd have to define divisible, and this way we don't have to do that. An integer n is even if and only if n is equal to 2k for some integer k. And an integer is odd if and only if n is equal to 2k plus 1 for some integer k. So in other words, if we have any even integer and add 1 to it, we get to an odd integer. They alternate. Okay, so that's what we get from these two definitions. Now, there's a theorem here, right? This is a conjecture. Here, the conjecture is that the sum of 2 even integers is even. And here's the proof. Right? Suppose that m and n are any even integers. According to the definition of even, there are 2 other integers, r and s, such that m is equal to 2 times r and n is equal to 2 times s. So, if we substitute, we know that m plus n is equal to 2 times r plus 2 times s. The distributive property allows you to take 2 out, and so this result here must be even because it is equal to 2 times some integer r plus s. So here is now the statement of that theorem. The sum of 2 even integers is an even integer. And that's the kind of thing we're working on now. Ideas. Now that was known as a direct proof because you went directly from the hypothesis to the conclusion. That's mostly the kind of proofs you've done up until now. And that's what most proofs are. Okay, so here is a summary of the method for doing those kinds of proof. So first, you express the statement to be proved in the form for all x in S. If this property applies, then this other property applies. And you do this mentally. You don't have to write that down. But you start the proof by supposing that x is any element of S. Right? For all x is in S, for which the antecedent p of x is true. What does that mean? It means your givens, right? The things you called in geometry the given, is this. If px, then qx, we're going to assume that px is true, okay, for any element in S. And then we're going to use the definitions of the terms and other known properties to make a chain of deductions ending with qx. And the chain of deductions is the kind of thing we just learned in the last section. We have those 3 valid kinds of arguments that we can use to create that chain. Okay, so here at the top here is a proof. This is the step-by-step proof, sort of like the way you did it in geometry, for what we just proved. M and n are any even integers, and then we get down to here and say m plus n must also be even. And you'll notice that this follows the law of transitivity. If this is true, then if m and n are any even integers, then this is true. And if this is true, then this is true. And if this is true, then this is true. And so you basically have a chain all the way down here, so it telescopes back together because of the law of transitivity. And you wind up with, if m and n are any even integers, then m plus n is even. Okay. All right. Example 2 down here. Suppose m is any even integer and n is any odd integer. And according to the even integer, you've got this. According to the odd, the definition of odd, you have that. So what do we wind up doing? What are we trying to prove? It's up here. If m is even and n is odd, then adding them together gives you an odd number. So we do basically the same thing we did up there, only this time you wind up getting the 2 distributed out, factoring out the 2, and then you have plus 1, so this is even. This has to be odd, right? Because we're adding 1 to it. Okay. Covering the reading. Okay. Show that the given integer is even or that it is odd. 270. If you divide that by 2, you can find an integer such that 135 times 2 is equal to 270. So that's the definition of even, having another integer such that when you multiply it by 2, you get the number you're looking for. Here, I can't divide this by 2, but I can divide 4874 by 2. And what I'll get is 2437. If I multiply that by 2, I get 1 less than this. I got to add 1 to this. That makes this odd. Here, interesting, minus 59. What's going to be the number here? Well, the answer is negative 30 is the integer we're looking for, because if you multiply that by 2, you get negative 60, and if you add 1 to it, you get negative 59. So showing that the given integer is even or that it is odd, in this particular case, it's odd, but the integer you're looking for is negative 30. Show the integer t is even by expressing it in the form of 2k for some integer k. Basically, what we're doing here is just factoring out a 2. The integer k would be a 3a plus 4b, because if we factored out a 2, 2 times that would equal t. A and b are integers and b is even. That means there is some integer k such that 2k is equal to b, which means that t is equal to a times 2k. Law of the associative property of numbers, of multiplication. T is equal to 2 times a times k, and a times k is an integer, so that makes it even. Here, suppose r and s are integers, and show that the defined integer is odd. Here, we know this is even because this is 2 times 5 times r times s. Okay, that makes this even. And we know that the sum of 2 even integers is even. So this is 6 plus 1. So what we wind up with, and maybe this is worth writing down here so you can see it, 10 rs plus 7. Okay, that's the same as 10 rs plus 6 plus 1, or 10 rs plus 2 times 3 plus 1. And if I factor out a 2 here, I get 5 RS plus 3 plus 1. I know that this is even because this is an integer and it's multiplied by 2. And then I'm adding 1 over here. Another way to think of this is to say 10 RS is even because I know it's the same as 2 times 5 RS plus 7. I know that 10 RS plus 6 plus 1, right? 6 plus 1 is 7. I know that this is even because it's 2 times 3. I know that the sum of two even numbers are even. So even without knowing what the value is, I know this has to be some number 2 times k because this is even, and I haven't used k yet, so 2 times some integer is equal to this. And if I add 1 to it, that makes it odd. So there are a couple of ways to go about proving that. This one here, how do we know that the defined integer is odd? Basically, we have the same thing we had a moment ago. Right? This is 6r plus 4s squared plus 3. It's going to be 6r plus 4s squared plus 2 plus 1. Factor out a 2 here, I have 2 times 3r plus 2s squared plus 1 plus 1. I know this is an integer multiplied by 2, which makes this whole thing even, plus 1 is odd. Okay. Definition of an odd integer using two if-then statements. So, okay, for all integers m, if there exists an integer k such that m is equal to 2k plus 1, then m is odd. And for all integers m, if m is odd, it means there exists an integer k such that m is equal to 2k plus 1. Okay. 9. Supply the justifications for these conclusions in the proof of example 2. They're asking for, right, how did we get to this? Right, that's A, and that's by the definition of even and odd. And then the question is, how did we get from here to here? And that's by the distributive property. Or we factored out a 2, which is part of the distributive property. So that's what it asks you to do here. The justifications for these conclusions. We actually did this, I think. Supply the missing steps in the proof of the following theorem. If m and n are any odd integers, then m plus n is an even integer. So first, suppose that m and n are odd integers. Right? That's the first thing we do. Thus, there exists integers r and s such that m is equal to 2r plus 1, and n is equal to 2s plus 1. That's the definition of odd, right? According to the definition of odd. Then m plus n would equal 2r plus 1 plus 2s plus 1, right? So if you put that together, it would be 2r plus 2s plus 2. And if we factored out a 2, it would be 2 times r plus s plus 1. And because of the definition, because what is an integer? Because r plus s plus 1 is an integer, m plus n is an even integer, because 2 times r plus s plus 1, 2 times some integer, is an even integer. And so that's the proof there. considering the following conjecture. If C and D are any even integers, then C minus D is an even integer. If you were to prove this conjecture with a direct proof, what would be an appropriate sentence with which to begin the proof? And it would be, suppose C and D are even integers. Okay. And what statement must you then show true? The statement is that C minus D is an even integer. And of course we would do that by manipulating the arithmetic as we've done in all of the others. That's 1-7.